right, as we get started today, I want to begin by reviewing something from Algebra 1 and Algebra 2 that you learned. We talked about different types of equations. And most equations, like, I don't know, let's take something really easy like x plus 3 equals 7, are what we call conditional equations. This is a lie unless x is equal to 4. That is the condition under which that statement is true. And it's not that an equation may have only one solution. For instance, if we had x squared minus 7 equals 6x. Well, this would be true if x is equal to -1, or it would be true if x is equal to 7. Right? A quadratic equation, of course, is going to have two solutions, but unless x is -1 or 7, this is a lie. Conditional equations. There are conditions or a condition under which the equation is true. But if I have this equation, x plus 3 times x -1 is equal to x squared -3 positive 2x, it doesn't matter what you plug in for x. It's always going to be true. And we call that, anyone remember? An identity. An identity is an equation, if you write that in your notes, that is always true for any value. An identity is an equation that is always true for any value. And basically, an identity exists whenever both sides of the equal sign are exactly equal to each other. For instance, if you were to FOIL these two binomials, first, outer, inner, last. Well, yeah, of course, that's true. Now that we FOIL it, right? No matter what you plug in for x, of course it's going to be true because the two sides match. So in trig, if I said the sine of theta is equal to the cosine of 90 degrees minus theta, that's always going to be true for any value of theta. That's what we call a cofunction identity. It's true for any angle, doesn't matter what it is. Well, we're going to, in this chapter, chapter 6, begin looking at different types of identities that we're going to memorize and use to continue the logical development that we began in geometry last year. Several types of what I call the fundamental trig identities. We're going to talk about several different ones, but some of them are very basic and very fundamental, foundational really to the study of trigonometry. The first group are some that you should already have memorized. So underneath this heading in your notes, fundamental trig identities, I was going to say ID. Remember, number one are what we call the reciprocal identities. The reciprocal identities. Again, these are identities or equations, if you will, that are true no matter what you plug in because, again, an identity is the essence of what something is. So, for instance, to say that the sine of theta is equal to 1 over the cosecant of theta, that's always a true statement because that's what defines, if you will, the cosecant in a sense. Conversely, cosecant theta is the reciprocal of the sine. We could, of course, say that cosine of theta is equal to 1 over the secant of theta, and conversely, the secant is 1 over the cosine. These are already memorized. You shouldn't have to spend a lot of time working on these. We could also say, if I could come over here, that the tangent of theta is equal to 1 over the cotangent, and conversely, that the cotangent is the reciprocal of the tangent. Make sure you have these written down. All 6, yeah. So these are your reciprocal identities. Again, these should not take much time for you to memorize. We pretty much already memorized them. A second set of identities, Roman numeral 2. Second set of identities that we need to memorize are what we call the negative angle identities. I cheat and use shorthand. Negative angle identities. These stem from the idea of even and odd functions. As we were graphing our different trig functions, we said that 2 functions were even. Which 2?
Sine and sine cosine and secant.
Cosine and secant were even functions. Now remember, an even function means that if you take a function of a negative, it's the same thing as the function of a positive. But an odd function, which we just discovered were all the other functions, an odd function, remember, if you take the function of a negative, it becomes the negative of the function. So sine of negative alpha, since sine is odd, must equal negative sine alpha. But cosine of negative alpha just equals cosine of alpha. The negative goes away. On the sine, because it's an odd function, it's as if the negative moves to the front. But on the cosine, it just vanishes. Tangent is also odd. So tangent of negative alpha must equal the negative tangent of alpha. Cotangent is also odd. So cotangent of negative alpha class must equal
cotangent
negative cotangent of alpha, because it's odd. The secant of negative alpha. Well, secant is even. So therefore, secant of negative alpha class must equal
secant alpha.
Secant alpha. But cosecant, which is odd like most trig ratios, cosecant of negative alpha must equal negative cosecant alpha. These are going to be very useful for us. The ability to just get rid of a negative, or to at least move the negative out to the front so we don't have to mess with it. No longer do we have to add 360 to negative angles. We just either slide the negative out front or make the negative disappear. Okay, so that's going to be very helpful for us as we move forward. Another set of identities that we need to have memorized that we have actually already looked at once before, though we didn't memorize them yet. In fact, I told you we're going to revisit these later and memorize them later, are what we call our quotient identities. Our quotient identities. Now, when you think quotient, going back to even your elementary days, honestly, you think what?
Addition. No.
Division, right? We had the sum is the answer to the addition problem, and difference the answer to the subtraction problem, and product the answer to a multiplication problem, quotient the answer to a division problem. So these identities are going to have something to do with division. Well, how do we show division in algebra? Fraction bar. So these are going to be some identities that have something to do with fractions. The first is that the tangent of phi is equal to the sine of phi over the cosine of phi. The first is that the tangent of phi equals the sine of phi over the cosine of phi. By the way, the angles are just whatever Greek letter I think of at the moment. Okay, so it's not that you specifically have to have one particular symbol. I just happen to go with theta, and I'm like, I should mix it up. Alpha popped into my head. Phi popped into my head, okay? So now the tangent equals sine over cosine. I showed this before, but tangent's what over what, class? Sine is what over what?
Opposite of hypotenuse.
Cosine's what over what? And we would form a complex fraction here in this quotient, wouldn't we? But we never really divide fractions. We multiply by the reciprocal.
Oh, the h's cancel.
And that means that O over A equals O over A. So that was kind of the proof that we used to show this. But we've probably seen this before anyway. For instance, on a 3, 4, 5 right triangle, if I found the sine of, let's just call this beta, if I found the sine of beta opposite over hypotenuse 4 to 5, the cosine of beta adjacent over hypotenuse 3 to 5, and the tangent of beta opposite over adjacent 4 to 3, oh, you mean 4 to 3 sine over cosine and allow the 5's to drop out? So a shortcut I suppose we could use. Now if that's true for the tangent, the reciprocal of tangent is cotangent. The cotangent of phi then must equal the reciprocal cosine phi over sine phi. And so we have just 2 quotient identities. We have 6 reciprocals, we have 6 negative angles, but only 2 quotient identities to memorize. And then the last set of identities, by far my favorite, we use them a lot, or we will use them a lot, are the Pythagorean identities. The Pythagorean identities. Now there are 3 of these, and again, we looked at these. In fact, you might remember a quiz in which the bonus question said, write one of the 3 Pythagorean identities. And we really hadn't looked at it much. We looked at it briefly, but not much. And so we didn't do too great on the bonus, but that's okay. That's why it was bonus. I'm going to address the Pythagorean identities. I could use the opposite adjacent hypotenuse thing like I did before, or I could use the unit circle. I'm going to address it from the unit circle perspective. We know that inside the unit circle, if you draw any angle, let's pick a Greek letter.
Beta.
Beta. If we take any angle beta, and we draw straight down off a radius of 1, this is the sine line, that's the cosine line. And in a right triangle, leg squared plus leg squared equals hypotenuse squared. So the sine squared beta plus cosine squared beta has to equal 1 squared, or 1. There's your first Pythagorean identity. And I think I even shared the dumb, pickup line you probably shouldn't use. You're the cosine squared to my sine squared. If we got together, we could be 1. Anyway, yeah, don't go for a guy who uses that, Janie. Nerd all day.
Didn't you use them in your wife?
Of course not. No. All right.
Tries to look away.
She would not have gone for me.
She would have slapped you in the face and walked away.
He said it to her after they married. She's like, you're stuck now.
Yeah. After she's married, I use all the nerdy pickup lines on her because she can't get away. All right. Now, another triangle we could form, we could come up here with the tangent line. Wherever we happen to stop on the angle, beta, we would have the secant functioning as the hypotenuse. And of course, this line here, of course, is the radius of 1. Well, again, we could say that 1 squared plus tangent squared equals hypotenuse squared, or secant squared. And there's our next Pythagorean identity, that 1 plus the tangent squared equals the secant squared. Again, if you know your unit circle, these Pythagorean identities are pretty straightforward.
Can't we technically say just 1? You took off the 1 squared. Because I was saying, can't we technically just say 1 plus whatever instead of 1 squared?
Well, yeah, I didn't write squared. I say squared so we understand the Pythagorean theorem here, but yeah, I'm not going to write a 1 squared because I'm lazy. You might also remember that for the same angle beta, here's the cotangent line up here, and its hypotenuse is the cosecant line. Of course, we have a radius of 1. So we could also say that 1 plus cotangent squared cubed squared beta equals cosecant squared beta. Notice that the last 2 identities are almost mirror images of each other. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. So they memorize together, I think, very easily. And this first one, if you remember nerdy pickup line, you got all 3 Pythagorean identities memorized fairly effectively. You're going to have these memorized by lesson 52, which is Friday. You're going to have these memorized by lesson 52. You're not going to have to use them by Friday or on a quiz by Friday, but you are going to have them memorized so that if I ask for the Pythagorean identity involving cotangent, you'd be able to write this. Or the quotient identity involving cotangent, you'd be able to write that. Or the negative angle identity involving cotangent, you'd be able to write that. Or the reciprocal identity involving cotangent, you'd be able to write that. Now, with whatever angle you choose, right? You could even choose a capital letter, right? For instance, normally in a triangle, QRS, you could say cotangent of R equals 1 over the tangent of R. You don't have to use Greek letters, but seems cool and nerdy if you did. What?
What is the sign for gamma?
Gamma?
Oh, that's why we don't use that.
Well, we'll use gamma a lot going forward. You'll get all and lambda's a favorite because like lambda or lambda, llama. Anyway,
Slumpda.
Anyway, so make sure you have these memorized by lesson 52 on Friday. Now, to help you memorize them, we're going to use them a bunch. And we're going to use them today for something that, frankly, given the choice of how to do what we're about to do, you ain't going to use these. There's a faster way. But the reason we're going to do it is we already know what we would normally do. Knowing then what the correct answers are, we can see how these work. So write this down in your notes now. The tangent of, let's see, what's a good Greek letter we don't use often? Let's go with lambda. Let's go with lambda, okay? The tangent of lambda equals negative 3/4. The tangent of lambda equals negative 3/4. and the cotangent of lambda is less than 0. Excuse me, the sine of lambda is less than 0. Now that wouldn't really help. The tangent of lambda equals negative 3/4, and the sine of lambda is less than 0. Given this information, we want to find the sine of lambda, the cosine of lambda, we already know the tangent, the cotangent of lambda, the secant of lambda, and the cosecant of lambda. Again, let me be clear. On a quiz or test, you would not do what we're about to do. You would say this is opposite over adjacent, you'd find the hypotenuse, you'd figure out the quadrant, you'd fill it in that way. But let's practice with our identities. If I know the tangent, the easiest other trig ratio to get by far would be its reciprocal, cotangent. So since tangent and cotangent are reciprocals class, cotangent of lambda must be negative 4 over 3. But if I know the tangent, I could use a Pythagorean identity. 1 plus tangent squared lambda equals secant squared lambda, right? And so we have 1 plus, now the tangent of lambda is negative 3/4. If I square that class, what do I get?
Positive 9 over 12. No.
9/16 equals secant squared lambda. But in order to add 1 plus 9/16, it'd be ideal to rewrite the 1 as a fraction. 16/16, which when added gives us class 25/16 is equal to the secant squared lambda. And now we've got to take the square root of both sides. Of course, square and square cancel. And secant, when we take the square root over here, is technically positive negative, right? Positive negative doesn't mean both positive and negative in this case. It means you have to make a choice. Do I choose the positive or the negative? Well, since tangent is negative class, I know I must be in either quadrant 2 or 4, but the sine is listed as less than 0, which means sine is negative, which means it's either quadrant 3 or 4, so we must be in quadrant 4. For this reason, I know I'm going to choose for secant the positive square root of 25/16. But what's the square root of 25/16? 5/4. So the secant must be a positive 5/4. Now again, yes, it would be so much faster the other way, but this gives us a chance to practice and use the Pythagorean identity. Of course, once you know the secant class, it'd be really easy to get its reciprocal. Cosine is positive 4 over 5. Now all I'm missing is sine and cosecant, and I want to go after the sine using the big 3. The big 3 are related in a quotient identity. That tangent of lambda is equal class 2, looking back in your notes.
Sine lambda over cosine lambda.
So if tangent equals sine over cosine, then that means, put this over 1, that to find the sine of lambda, I could cross multiply the tangent times the cosine, correct? And I already know that the tangent is negative 3/4. And I know that the cosine is positive 4/5. And I could cancel away the 4's to get negative 3/5. And once I know the sine, it'd be easy to use a reciprocal to get the cosecant to be negative 5/3. And there we go. Again, is this the fastest way? No. Would you do this on a quiz or test? No. Okay? But it gives us a chance to write out the identities and practice with them. Turn your textbooks to page 107. Let's do some more of these. Again, today is all about having opportunities to write out the identities, plug numbers into them, see how they tie together, and hopefully that will assist us in memorization as we look ahead toward the quiz coming up in lesson 52 on Friday. Let's take a look at number 3 in here. Number 3, we've got the tangent of alpha is 21 over 20, and we know that the cosine of alpha is greater than 0. Let's find the quadrant first. ASTC, Quentin, tangent is evidently positive, what quadrants could that be?
1 and 3.
1 and 3. But Jamie, it also says that cosine's greater than 0, which means cosine is positive. And cosine's only positive in
first and fourth.
First and fourth. So evidently, class, we are in quadrant 1. Which means everything's going to be positive. Now, for the most part, the signs take care of themselves, except on the Pythagorean identities, where you're going to end up taking square roots. That's the reason we need to know the quadrant. Otherwise, we find sine of alpha, cosine of alpha. You're writing this down as well. We already know the tangent of alpha, the cotangent of alpha, the secant of alpha, and the cosecant of alpha. Everybody's going to be positive. That's happy. What's probably the first trig ratio we ought to find? Ethan? Cotangent, because it's so easy, right?
Yeah.
Which is? 20 over 21. But then you got Chris over here, and Chris is like, I'm a rebel. I don't want to find the first one that's really easy. I want to do things the hard way, my way. And so Chris is like, I know that tangent also is in a Pythagorean identity.
Yeah, it's an 1 plus tangent squared equals secant squared.
And going with alphas here.
Alpha.
And so tangent squared, you shouldn't need your calculator here, right? We memorized that 21 squared is 441, right? It's the backwards of 12 squared, right? 12 squared is 144, 21 squared, 441. We know that 20 squared is 400. And while we're at it, let's rewrite the 1 as 400 400ths, all equal to secant squared alpha. No, let's take the square root. If we add these together, I get 841 400ths. And, oh boy, well, I know the square root of the 400 is going to be 20. What about the square root of 841 on the calculator?
29.
So there we go. And normally positive, negative, right? But I'm choosing the positive because it's in quadrant 1. So I know the secant is 29 over 20. And then you may have Jamie over here. It's like, ooh, not to be outdone. Cotangent is also in a Pythagorean identity. Which one, Jamie?
Cotangent, let's see. It is 1 plus cotangent squared alpha equals cosecant squared alpha.
There we go, because we know the cotangent is 20 over 21, and if we square the 20 over 21, we'll get
the 400 over 441.
Which means I don't want to write 1 as 400 400ths, class. I want to write it as
441 over 441.
Again, you're doing this with me. And that's going to be the cosecant squared alpha. I'm going to take the square root. And so what does my fraction become under the radical, Ethan?
841 and 441.
And I'm going to choose specifically the positive square root here, which is? We just did the square root of 841 a minute ago.
29 is the top one.
And the square root of 441 we just got a minute ago, or used a minute ago. Yeah, 29 over 21. And from here we could, how would we get either sine or cosine, Ethan?
We already have secant.
So we could get the cosine,
20 over 29.
20 over 29. And of course the easy way to get the sine, class, would be to take a reciprocal. But Quentin doesn't like the easy way. Quentin's like, no, I want to use my own Pythagorean identity. So Quentin uses the other one we ain't used yet.
Imagine not getting one yet.
It's coming, it's coming.
Sine squared alpha plus cosine squared.
All right, and so I don't know the sine of alpha, but since I'm solving for it, I'm going to move the cosine over as a negative cosine squared alpha. And I know that if I square 20 over 29, well, 20 squared,
400.
and 29 squared we've seen a couple times, 841. So I know I'm going to get a 400 over 841. And I should probably rewrite the 1 as
841 over 841.
right, and when I subtract 841 841st minus 400 841st, I get
869 over 841.
441 400 or 800 or 441 841st. There we go. And that's the sine squared alpha, so I'm going to want to take the square root. And we know the square root of 441 by now is
121.
21. And we know the square root of 841 by now is 29. And of course, it would have been way easier to just flip the cosecant, but that's not how Quentin does things. He likes to do things the hard way. And I'm just picking on you. Questions on this? Again, I normally would use reciprocals. Actually, I would normally do this the other way anyway. Let's take a look at number 5. Oh boy, calculator's ready. We've got the cosecant of theta is negative 85/77, and the cosine of theta is less than 0. Ethan is feeling left out over there, so Ethan,
take him to the whole problem.
Chris, what quadrant are we in?
Okay, so cosecant is positive.
Oh, it
Or
is?
cosine is positive, cosecant is negative.
Cosine's positive?
Yeah, it's great.
Less
It's
than 0?
So it'd be sine. No, sine's negative too. So it'd be tangent and cotangent are positive.
Okay, so he basically came to the conclusion, well, if cosine's negative, it's either second or third. Cosecant's also negative, so that's either third or fourth. It's got to be the third quadrant. So as we list these out, the sine of theta, the cosine of theta, the tangent of theta, the cotangent of theta, the secant of theta, but certainly not the cosecant of theta. We already know that one. We know that the only ones that are going to come out positive, class, are the
tangent and cotangent.
Tangent and cotangent. An easy function to get first, Chris.
Would be your sine.
Yeah. Do we want to do the easy one first? What? Of course. What do we get?
77 over 85.
Well, negative 77 over 85. And hey, if we got the sine, I could also find, Ethan, the cosine by using what? It's great for getting answers, but it's bad for getting girls. Oh, come on, Ethan.
Sine squared theta plus cosine squared theta equals 1.
There we go. Where if I'm trying to find the cosine, I'm going to need to move over, class, the sine squared as a negative sine squared theta. So we've got that the cosine of theta is equal to the square root of, because I'm too lazy to do it later, and I need to square the sine. This is where the calculator is really helpful. Let's square the 85.
7,225.
7225. And let's square the 77. 5929.
Yep.
How do we rewrite the 1, Ethan?
7,225 over 7,225.
And when we subtract, we're going to end up taking the square root of how many 7,225ths?
1,296.
All right, we'll go back to Ethan here. What is the square root of 1,296? There we go, 36. And we already know the square root of 7225 is going to be 85 we started with. And do I choose the positive or the negative for the cosine since we're in quadrant 3?
Negative.
We're going to choose the negative 36 over 85. Hey, if we're going in order, we could find the tangent next. But Ethan, how would we find the tangent if all we have is sine and cosine? It's not a Pythagorean identity.
Well, it is. We have tangent and, or sine and cosine, so we can use tangent theta equals sine theta over cosine theta.
Yeah, use the quotient identity. Tangent equals sine over cosine. Where I have the sine as negative 77/85. I have the cosine as negative 36/85. And watch what happens with the SIGN here. Negative divided by negative, class. Positive, which I already knew would be the case, but mathematically it works. And then 85 common denominators cancel, and my answer comes out to
77 over 36.
the 77 over 36. Let's go in order. Let's find the cotangent next. How would I do that? Ethan?
We can do the cotangent of theta equals cosine theta over sine theta.
Cotangent theta equals cosine theta over sine theta. where I already said that the cosine was a negative 36/85, and the sine was a negative 77/85, which gives me what?
36/77.
Positive 36/77. Or the easier way, anyone?
Reciprocal.
Just take the reciprocal of the tangent we just found.
Yeah.
How can I find the secant here, Ethan?
Reciprocal.
Reciprocal of the cosine. But let's suppose Ethan's like, nah, I want to do things the hard way, Mr. Nadasky. What's the other way we could find the secant?
We can do 1 plus tangent squared theta equals secant squared theta.
There we go. And so I know that secant of theta is going to end up being the square root of 1 plus tangent squared. Well, by now we've seen all of these numbers. When I squared the 77 earlier class, I got 5929. When I squared the 36 earlier, I got 1296. So I know this is going to be 5929 over 1296, which means I need to rewrite the 1, Ethan, as
1296 over 1296.
And Ethan really wishes we were doing the reciprocal method, but in his heart of hearts, he really wants to do this because it seems cool and interesting. And so he's going to add the 1296, 1296, plus 5929, 1296 to get
72. Okay, Ethan.
Don't bother writing the denominator. You already know what it's going to be. Just add the numerators.
Yeah, I should do that.
You should have did that. Yes, that would.
The answer is 85 over 36.
Well, yeah, but what do we get when we add 1296 plus 5929? Good, Chris. 7225 over 1296, and we need to take the square root of that, of course. And we end up getting what, Ethan?
85 over 36.
85 over 36. But we're going to have to choose positive or negative, and in quadrant 3 we choose the negative, which we would have seen if we had. I guess would have sawn is technically correct grammar, but only if you're talking about, like, the magic trick sawing a little girl in half. I would have sawn her in half, but she ran away. I don't know, whatever. I would run away too. All right, especially if it's an amateur magician. All right, questions on this?
She'll be running if she's cutting half.
This is before she was cut in half. I would have sawn her in half, but obviously I did not because she ran away. All right. Anyway, I want you to do number 9, and you don't have to do things the long way. You can do things the easiest way possible.
Can I finish this game for you?
Yeah, do number 9.
Which means I can find whatever we're missing and just do it that way.
Well, no, using identities, but you basically do at least 3 reciprocals.
He knows we can do it that way. He wants to know if we can do it this way.
Well, the more I want you to practice with these, so it'll help you memorize them for Friday and beyond, of course, because we're going to use these in other ways beyond the quiz on Friday. Oh, much more. Many more ways.
Is W omega?
Omega, yeah. The W-looking thing is a lowercase omega. So, if you're talking about root beer, A and W root beer is actually the beginning and the end, the first and the last, alpha and omega root beer. Except they do capital A, which is actually capital alpha, but they don't do this omega. The capital W is not a Greek letter. Anyway,
they didn't do that on purpose, did they?
No, they didn't. Probably 2 guys' names, one who started with A and one who started with W, so they call themselves A and W. Which is good root beer, by the way. IBC is pretty good, too.
It's way better than Barks.
Barks is awful.
Yeah,
now. Mug is even okay, but not Barks.
Barks.
Barks is nasty, bro.
It's nasty root beer.
I don't like any root beers, so.
Yeah, Culver's root beer is acceptable as well.
It's acceptable. It's not exceptional, it's acceptable.
Exactly. You're doing number 9. Hopefully doing at least an acceptable job on it. It'd be better to do an exceptional job on it. Again, I would use at least 3 reciprocals. Well, not at least 3. I would use 3 reciprocals, and then either 2 Pythagoreans or a Pythagorean and a quotient. checketh thy work. First thing I did, figure out what quadrant we're in. Figured out it was quadrant 4, how many good to go there. All right. Then the first thing I got was cosine, because that's just an easy reciprocal, 28 to 53. The second thing I found was the tangent, which I based off of the secant, and I went with the tangent, 1 plus tangent squared equals secant squared, moved the 1 over, took the square root of, well, that's 53 to 28, that has to be squared, minus what's going to be 28 to 28 squared. End up getting big numbers, subtracting, take the square root, end up getting for number 2, my tangent, negative 45 to 28. Well, that's an easy reciprocal, then I get negative 28 to 45. I then went back to the tangent and the cosine, which I found first and second, and I found the sine fourthly. I cross multiply to get sine equals tangent times cosine, plug in the numbers, cancel the 28, boom, there's negative 45 to 53, and just take the reciprocal to get negative 53 to 45. So 1 Pythagorean, 1 quotient, 3 reciprocals, and there are my answers. How many have these answers on this one?
I didn't get the sine and cosine, but I had all of them, or I didn't get the sine and cosecant, but I had all the ones I did right.
All right, makes sense how to get sine quickly?
I would have got it right.
All right, let's go on and do that was number 9. Let's do numero 10. Oh, yes. Number 10, match seats. Again, reciprocal, probably Pythagorean. Reciprocal, either Pythagorean or quotient. And then reciprocal to finish out.
Here's my three.
Go. Numero 10. Mix it up this time. Don't use the same Pythagorean you used last time. So my Pythagorean last time was the 1 plus tangent squared equals secant squared. I'm going to use a different one this time. Help me memorize all of them. For sake of time, go and stop where you're at. Did you find the cosine first, I hope? -7 to 25? Can't get easier than that. Now, I've got either of these I can use in a Pythagorean to get, if I use cosine, sine. If I use secant, I would get tangent. Well, last time I did secant to get tangent, so this time I did cosine to get sine. And ended up getting the sine to be 24 to 25. Chose the positive because of quadrant 2. Once I got sine, reciprocal, 25 to 24, one of those. It's like when your mom tries to call your name and you've got a lot of siblings and all the names come out. Anyway, 25 to 24. Well, once I got sine and cosine, by the way, I could also easily get either tangent or cotangent. Well, last time I did the tangent quotient identity, so I wanted the cotangent to mix it up and do cosine over sine. And I canceled the common denominator, get -7 to 24 for the cotangent. Then I flipped that to end on the tangent. And again, you didn't have to go in that order necessarily, but did you get the same answers using identities? 3 reciprocals and either 2 Pythagorean or a Pythagorean and a quotient. I feel like you're getting the feel of these identities. Also, getting the feel of moving things around and rearranging. It's going to be big for where we're going next with this. So again, this is not an end unto itself. This is not normally the way you would do this, but it gives us practice with the identities at a really low baseline understanding level to help us do better tomorrow when we step it up a notch. What?
Pythagorean, my favorite.
Pythagorean? All right, again, calculator is definitely a blessing. Your homework this evening is to copy your fundamental identities one more time. Okay, you've already copied them out once. Copy them out one more time. And then do page 209, numbers 8 and 14. Page 209, numbers 8 and 14. I'm giving yourself some more practice. Again, don't do them the easy way you would do on a quiz or test. So if you ever saw those on a quiz or test, do them the easy way. I'm never going to tell you on a quiz or test to do them the hard way. But get the practice on page 209, numbers 8 and 14.
209? Or is it 107?
How about 107? I don't know where 209 came from. That's a good question. Where did I get 209?
I was like, when did we get there?
Let's try page 107. I don't even know where 209 came from. I don't see a 209 anywhere on here.
What is a 209?
A 209 is something that comes right after a 208.
And before.
No, after 107.
All right, page 107. Try numbers. Let me read them again. Make sure I don't screw this up. 8 and 14 is your homework. All right, we'll take a look at that in our next lesson. And then we'll get where we're really going with this tomorrow.